Hey there, welcome to the video. Today we are diving into something really cool, independent component analysis or ICA for short. If you have ever wondered how we can separate mixed signals, like pulling apart different voices recorded in a crowded room, ICA is the magic behind it. I will walk you through what ICA is, how it works, a simple simulation to make it crystal clear, and then we'll get into one of the fastest algorithms for it, fast ICA. All right. So, what exactly is ICA? At its core, ICA is a method that takes a bunch of mixed signals and tries to pull out the original independent sources. Like, imagine recording in a room where multiple people are talking. Each mic picks up a mix of all voices. ICA helps you untangle them and isolate each one. Now, to do that, it makes a few assumptions. The original source signals must be statistically independent, and the second one is, except for at most one signal, the source components must be non-Gaussian, and it is often assumed that mixing matrix is square for simplicity. So here is the setup. We have observed signals x of t, which are essentially mixtures of unknown independent source signals s of t. Our goal is to separate these mixed signals back into their original independent components. To do this, we assume the mixing process can be described by a mixing matrix A, but we don't actually know A or the independent sources s of t. All we have are the observed signals x of t. Using the ICA approach, we aim to find demixing matrix W that allows us to separate the mixed signals and recover the independent components. This is the power of ICA. With just the observed signals and the assumption of statistical independence, ICA allows us to recover the original sources even without knowing that exact mixing process. Now, let's take a quick look at how fast ICA works. This is the actual algorithm that makes ICA super fast and practical. Now we start with input data. First we center it and then we whiten the data. Then we initialize some weights and this is where the magic begins. We go through three steps. Fixed point iteration, where we update the weights to make the signals more non-Gaussian. And then the orthogonalization, where we make sure each new signal is independent from the others. And the third one is normalization, where we scale the weight vectors to keep things stable. If things haven't settled down yet, we go back and repeat the steps until the weight stops changing. Once they converge, we have got our separated signals. Now we'll look at a small ICA simulation. For full code and interactive execution, access the Google Colab. So first column, these are original signals I made. There's a smooth sine wave like brain activity, sharp spikes like eye blinks, random muzzle noise, and a heartbeat like pulse. In the middle, you see what we actually observe in practice. These are the mixed signals. Looks very messy, right? And now the last column. This is the output after running fast ICA. Pretty amazing. The original signals are mostly recovered. Now they might be in different order or even flipped upside down. That's totally normal. ICA doesn't know what signals comes first or which way is up, but it does recover the independent shapes, and that's what really matters. Let's now unpack the steps we saw in that block diagram earlier, starting with the centering and whitening. Centering means subtracting the mean from signals, making the average zero. Whitening is like reshaping the data so all the components are uncorrelated and scaled nicely. This helps the algorithm focus on what's truly unique about each signal. Now let's look at the core part of fast ICA algorithm, the fixed point iteration. Recall that our ultimate goal in ICA is to find the demixing matrix W so that we can recover the independent sources from the observed mixtures. To find each row of this matrix, that is, the each weight vector W, we use this iterative method. The idea is to choose W such that when we project our data onto it, the result should be as non-Gaussian as possible. This update rule here is what helps us to do that. After each update, we normalize this vector. This helps the algorithm stay numerically stable and ensures convergence. Once we find one component, we want to make sure the next one is different from it. That is, the next one is totally independent of the previous component. So we use orthogonalization for that. In simple terms, this step ensures that As we keep finding new independent components, each one is distinct and doesn't overlap with the others. One way of doing it is using this deflationary scheme. If we want to perform even more efficient orthogonalization, we can decorrelate all the components at once. This is called symmetric decorrelation. One way to do this is with something called matrix square root method. Sounds fancy, but it just means we are adjusting the weight matrix to keep all components independent together. It uses eigenvalue decomposition. There is another method that's even more simpler than the previous one, especially for large datasets. Instead of calculating matrix roots, we just iteratively update the weights and normalize them until they converge. This was introduced by the guy who created fast ICA, and it's very super efficient. We have now covered the essential structure of fast ICA algorithm, beginning with the centering and whitening, followed by the fixed point iteration for estimating independent components, and the orthogonalization to enforce mutual independence. A crucial part of this process is normalization. After each update, we scale the weight vectors to unit norm. This maintains numerical stability and keeps the optimization well behaved. These steps are repeated until convergence, that is, when the weight vectors no longer change meaningfully across iterations. With these steps complete, we obtain the independent component. Now that the algorithm is fully understood, let's move on to the key properties of fast ICA. It's super fast, much faster than the traditional gradient methods because of cubic convergence. And there is no need for learning rates. You can extract one component at a time or all at a once. It's easy to implement and it works well even on large data sets and even in real time. To truly understand why it works so well, it's important to take a step back and look at the mathematical foundation behind ICA. Before we dive into math behind ICA, let's clarify a key concept. Independence means that knowing one variable tells us nothing about the other. Formally, their joint expectation factorizes for all functions. A weaker condition of independence is uncorrelation, where only linear relationship vanishes, that is, their covariance is zero. It's important to note that independence always implies uncorrelation, but the reverse is not true. As we saw earlier in the code output, ICA introduces certain ambiguities, specifically variance and order ambiguities. These are very common challenges and we have already discussed them when interpreting the results of simulation. You can go through this slide for more details. Using the central limit theorem, we can prove that by maximizing non-Gaussianity, we effectively isolate the independent components of the mixture. You can go through this slide for better understanding. Now, let's take a look at some measures of non-Gaussianity. One common measure is kurtosis. Kurtosis tells us about the tailoredness of distribution. If kurtosis is 0, the distribution is Gaussian. If it's greater than 0, the distribution is super Gaussian and has heavy tails. If it's less than 0, it has lighter tails and the distribution is called sub-Gaussian. We maximize non-Gaussianity by maximizing the absolute value of kurtosis, which helps us identify how far the distribution is from Gaussian. We do this by adjusting the components of projection. However, kurtosis is sensitive to outliers, making it less robust. This is why we often use more robust measures like negentropy, which we will explore next. Negentropy measures the difference in entropy between a signal and its Gaussian counterpart. It is always non-negative and maximized for non-Gaussian signals. While it's a very good measure, it's computationally very expensive. So we use approximations to make it more feasible. To approximate negentropy, we use two main approaches. The first is the moment-based approximation, which uses higher order moments like the third order moment and kurtosis to estimate negentropy. However, this method shares the same limitations as kurtosis, such as sensitive to outliers. So we go to general non-quadratic function approximation, which uses a non-quadratic function g of y to approximate negentropy. It compares the expected value of g of y for the signal y and a Gaussian signal n. These approximations are both computationally efficient and effective, providing a more robust alternative to kurtosis. From these functions of non-Gaussianity, only we derived the fixed point iteration update rule used in fast ICA. Having covered the math behind ICA, now we look at why Gaussian signals are forbidden in ICA. Gaussian signals are symmetric, and this symmetry causes a lack of directional information, preventing ICA from uniquely identifying the independent components or the mixing matrix unless at least one source is non-Gaussian. Let's now take a look at where ICA is actually used in the real world. So, where is ICA used? In brain signal processing for separating brain waves from eye blinks or muzzle noise, in finance for pulling out hidden market factors, for image denoising, uh, for doing separating signal from noise, and in telecom to extract individual messages from a mix of signals. Conclude, independent component analysis is a fundamental technique in signal processing, enabling the separation of observed data into independent components by harnessing the principles of non-Gaussianity and latent variable models. The fast ICA algorithm, in particular, offers a computationally efficient and robust method for this task. ICS diverse applications ranging from brain signal processing to telecommunications underscore its broad relevance in modern data analysis. And this is the reference we used for preparing these slides and presentation. Thank you for listening.